is the center of mass and scale for incoming particles. Actually, if we consider this limit, actually the produce the random pair take the most of energy from the incoming particles. So the remaining hadron final state becomes soft. Also, the hard part becomes shrunk. In only include the virtual iterations between incoming two particles. So finally, we have a much more complicated factorized formalism for structure functions. We roughly estimate that these structure functions could be factorized as a hard part and soft part. Soft part describe the final state of soft radiation, and maybe along the directions we have the two pattern distribution functions right there. Okay. The proposal of this talk is to prove that that kind of factorized formalism for the structure functions near the endpoint region is Christian. Okay. So in that case, near the endpoint region or threshold region, actually we have the three scale hierarchy. The right scale is Q, and the second right scale is Q times 1 minus G, and finally we have non-distribution, right? Okay. So if we employ the effective field theory approach, actually, because we have three scale hierarchy, we have to take the step-by-step matching step. Actually, to begin with, around the scale Q, innovate our hard degree of freedoms, we can obtain parallel hard functions. And then also simultaneously we can match full QCD onto the effective field theory. Here I choose the typical example of the effective theory as a soft Korean effective theory. Okay. Anyhow, and then we can scale scale down to the Q times 1 minus G. Actually, around that scale, we can also innovate out the fluctuation of Q times 1 minus G. And then we can obtain this infinite finite, the second step matching coefficient. Okay. So these two Wilson coefficients or matching coefficients should infinite finite. Okay. Also, if we employ the soft collinear effective theory, we have some benefit. Actually, performing the scale evolution of these two Wilson coefficients to the lower factorized scale, we can automatically discern the large logarithm. Actually, near the endpoint region, we can always face that kind of large logarithm over 1 minus G. So at the fixed order in alpha S, we cannot obtain the precise region. In principle, because of the presence of this logarithm, we have to listen this logarithm order in alpha S. In SCET, simply solving the normalized complications, we can automatically listen large swath logarithm. Anyhow, finally, at the factorized scale, we can obtain these two pattern distribution functions. As a QCD does in effective field theory, all the infinite diagonals should reside in these two pattern distribution functions. Okay. Okay, this is our desirable effective field theory description for the search function near the endpoint region. Okay, here is I briefly introduce soft collinear effective theory. Soft collinear effective theory has been developed for describing the strong interactions for energetic and soft particles with the systematic power quantities. For example, if we consider n collinear system, here is n and n bar is two radical vector. Actually, n bar is the opposite direction of the n direction. Also, I brought this normalized condition. So if we consider the n collinear system, the n collinear particles momentum can be decomposed as follows. Here eta p is the largest component, and p pop is the second largest component, and eta p is the smallest component. Here also we introduced the small power quantity parameter. Okay. So with this small power quantity parameter, we can successfully decompose the collinear star, and then we can successfully construct the collinear field. Right? If we write down collinear Lagrangian at the leading order in lambda, we have also the leading interactions with all collinear particles. However, if we compute the infinite soft Coulomb radiation, actually we can successfully decouple the kind of soft Coulomb interactions from the collinear field. Okay. In other words, fortunately, we can exponentiate the kind of soft Coulomb radiation. The kind of soft Coulomb radiations. As a result, we can obtain the following soft resonance. Right? And then redefining the collinear field right there, we will have a collinear field which do not interact with the soft particles. In case of Drell process, actually, integrate out hard fluctuations, we'll have the three field contents by kinematic regions. Actually, after integrate out hard field freedoms, this N collinear field and the M collinear field, actually, this is another collinear field in the opposite p directions, and so they do not interact with each other. Also, finally, we'll have three field contents by kinematic regions. Each field do not interact with each other. So in SCET, at operator level, we can successfully separate the N collinear interactions and M collinear interactions and soft interactions right there. So applying soft collinear effective theory, we can obtain the following factorization for the structure functions. Actually, after iterating out hard degree freedoms around the scale Q, and then at the operator level, we have three separated field contents. So simply taking the matrix element, we can obtain the soft functions and the convolution of the two collinear functions. In SCET, the soft functions can be described as follows. That can be described by soft Wilson line. Actually, this soft function describes the soft Bloom radiation in order of static amplitude. Actually, at the location of the unity curve, I just put the delta functions. If we take the period transformation, we can obtain a value non-local expression for the soft functions. Also, similarly, we can also obtain the following collinear functions, assuming this collinear function shares the same definition as the pattern distribution functions. So far, so many guys just identified this collinear function with the standard pattern distribution functions. But before we identify this collinear function as pattern distribution functions, we have to check one point. If this soft function is infinite finite. Okay. For example, if the collinear function is indeed pattern distribution functions, and if this soft function is infinite diagonal, we can't reproduce infinite diagonals in proof C, because in proof C, all the infinite diagonals is located in two pattern distribution functions, right? So I showed the computation about the soft function expression here. Here, diagram A represents the virtual one diagram, and the diagram B represents the concept Bloom radiation. Okay, so here is I just regularized all the UV diagrams and the IR diagrams using the dimensional regularization, right? So if we identify usually UV and usually IR, actually this virtual diagram gives the result 0. However, this is not the express 0 if we distinguish UV and IR carefully. The surprising thing happens in the diagram B, in the concept Bloom emission diagram. Actually, here we have some several diagrams, singularity. But these singularities turn out to be, all the singularities turn out to be infinite diagrams. So when we combine these two together, we cannot obtain the infinite finite region. So this seems problematic. So as a result, this result implies that this collinear function would not be pattern distribution functions. Actually, we have to take these collinear functions somewhat different than the pattern distribution functions. Actually, the main difference is closely related to the double count problem. Okay, so why is double count problem? Even though at the operator level, even though we decoupled soft fields from the collinear field successfully, in actual computations, we have to worry about the double count problem. For example, if we perform the collinear one calculations, actually this collinear one room momenta can be always taken as the order Q, right? However, this room momenta can touch it from 0 to infinity. this room momentum is around 0, actually this collinear room momentum becomes soft. Okay? So in actual computations, we have to subtract that kind of double counting stuff. So consistent computation for collinear interactions can be suggested as part of it. Actually, we can perform diagonal calculations, and then we have to subtract some contributions when the room momentum becomes soft. Okay, this is called as the German subtractions. Actually, it is first found by Nana and Stewart in 2007. Okay. So actually, I realized that the main difference between the collinear function and pattern distribution functions comes from the German subtractions. Actually, in this factorized formalism, we already have collinear functions. Okay, these collinear functions have to worry about double count problem with the distinct functions. This typical scale is given by Q times 1 minus G. So we have to perform that kind of soft German subtractions. Actually, at the lower energy scale, then Q times 1 minus G, when you compute the one corrections to the pattern distribution functions, we also have to worry about some kind of soft, some kind of double count problem with the very soft momentum. Okay. So in principle, for the PDF, we also have to subtract some German subtractions. However, in that case, this soft momentum is considered to be much smaller than Q times 1 minus T. So I call it the ultra soft momentum. Okay. So in summary, for the collinear functions, we have to perform the soft German subtractions whose scale is Q times 1 minus G. For the pattern distribution functions, we have to subtract the ultra soft German subtractions. Okay. So here is I showed the one calculation of the German subtractions. Actually, for the virtual computation, right there, the soft German subtraction contribution and the ultra soft German subtraction should be the same. But actually, the difference comes from the real conditions. Actually, when you perform the soft German subtractions, actually here x equals to 1. So if we consider the argument of the delta function, actually this is collinear room momentum, this is collinear room momentum compared to the 1 minus x times another p. So in this case, we will have the parallel in the trivial region. In case of ultra soft German subtractions, actually this collinear room momentum can be considered to be much smaller than another p times 1 minus x. Right? So in this case, in the argument, this room momentum can be safely ignored. So we have the parallel region. So with these delta functions, when you compute these German subtractions, actually the result should be the same as the virtual fractions, with the only difference is negative side. So for the ultra soft German subtractions, for the PDF one computations, actually when you combine the real and virtual fractions, actually those German subtractions can cancel. So for the PDF, direct collinear one calculation would be enough. However, for the collinear functions, because we have clean difference between these two, we have some non-trivial region. Actually, the collinear functions can be defined at the scale Q times 1 minus x. Here is x equals to 1. Here the threshold region, y the endpoint region. In this case, so because it can be because this collinear function is defined this scale. In this scale, actually this collinear function in principle can be matched onto the pattern distribution functions, right there, leaving this collinear kernel. Actually, this collinear kernel has a non-zero result because of the difference of the two zero subtractions. Okay. Actually, this collinear kernel can be considered to be another type of match coefficient. But complete says this match coefficient is not enough. The result is actually this collinear kernel involved some infinite diagonals. Okay. So this is also parallel. Anyhow, if we consider the collinear function of the blue field, actually we can can obtain the same result right there. Also, at the end of the day, this collinear kernel has the parallel result. Also, if we compare this collinear kernel of Hawk field and the collinear kernel of Blue field, only difference is the color Casimir effect right there. Anyway. So, when you match collinear function to pattern distribution functions, we have some problematic collinear kernel like that. It involves some different diagrams. However, we already have a problematic soft functions right there. So, when we combine this soft function and these two collinear kernel, but some surprising things happen. Actually, at the end of the day, after the recombinations, we can have different finite region right there. Okay, this is consistent with effective shield descriptions. Actually, this WDY can be considered to be the second matching coefficient around the scale Q times 1 minus C. So, including this region, the search function for factorization, the consistent factorization for search functions can be related. The hard function and the hard function is the first matching coefficient, and the WDY is the second matching coefficient around the scale Q times 1 minus G. And the final factorized scale, which can be considered to be much lower than the scale, we have two pattern distribution functions. Okay. So I extended my idea to the diminished scale in the endpoint region. Okay. So actually here I showed the search functions f1. So I just consider the search function in the limit x equals 1. In this case, in the final state, we have basically we have 1j. Also, we have soft law radiations. So applying soft collinear effective shielding, if we construct the factorized theorem, we have hard function and collinear function and jet function and soft function. Okay. If we identify this collinear function as the pattern distribution function, actually some problem happens. If we consider scale values for each function, actually we cannot satisfy this visual. Okay. But physically, this search function should be scaled in value, right? Also, finally, we can realize that this soft function will be on NTU. Okay. In order to cure this problem, actually we can also the same step. We can take the same step as the Dirac case. These collinear functions can be natural pattern distribution functions obtaining this collinear kernel. And then we can recombine this problematic soft function and the collinear kernel. Finally, we found that at the higher order in alpha s, this result gives the 0. So this W, DIS, gives a trivial result. And then we can rewrite the factorization for the search function in DIS like that. Okay. This satisfies this result, this condition. Finally, I have considered the Drell process with the small transverse momentum distributions. Okay, so here, if we consider the small transverse momentum of the random pair region, actually includes the random pair, take the small q. In this case, the soft part and the collinear part, I mean, the transverse momentum of the soft part and the collinear part can severely affect this PT distribution of the random pair. Okay. So in this case, if we construct the differential scattering intersection and if we construct the factorization of that, actually we should take a very complicated process. Also, like the threshold region or endpoint region, actually we have a 3-scale hierarchy. Okay, Q is the last scale and PT is the second last scale and lambda should be the smallest scale. Actually, I employed the same idea as the DBS scattering and Drell case without PT. Okay, so employing the soft collinear effective shielding, we have hard function and these two transverse momentum dependent collinear function and soft function. Okay. This collinear function and soft function will be problematic. Actually, it involves some different diagrams. Also, even if we consider the anomalous dimension, actually each anomalous dimension is infinite diagram. It's problematic because this infinite, because the anomalous combination is described only vividly without infinite values, right? In order to cure that kind of problem, actually we can match this transverse momentum dependent collinear function onto the standard particle distribution functions. Here is I just assumed that PT is still much larger than lambda QCD, so its PT is still part of it. Okay. So after taking this matching process, we can obtain this collinear curve, transverse momentum dependent curve, and then I just recombine this collinear dependent curve and soft function. As a result, I can obtain this infinite finite region. Okay. So finally, we can rewrite this factorization theorem for this difference scattering cross section, right? Okay. Hard function and transverse momentum dependent curve. Okay, which describe the early fluctuations of the PT. And finally, the lowest energy scale, we have the two particle distribution functions. So finally, solution is there. Actually, my idea is actually when you write down the factorization, theorem, for example, if we, for example, employ the interpretation approach, when to begin with, we can construct the live potential, and then actually we can easily find that this live potential does not consistent. So, in order to cure this problem, actually we have to worry about the double count problem, and then from the collinear functions, we can extract some collinear term matching onto the particle distribution function. So, in order to cure the double count problem, actually this collinear kernel has been introduced in order to cure this double count problem. But this collinear kernel is very useful. Actually, when you combine this with the soft part, we can get consistent, well-defined matching coefficient at the intermediate state. Okay, this is my vision. Thank you.
Question, comment, please.
In the ordinary PQCD calculation, we can show that the soft divergence in the PDF cancel. So we just get a single collinear logarithm. And certainly in this case, there's no soft function. Okay? The soft divergence also cancel. Yeah. But somehow in the SCET, okay, you need the soft function. And also your collinear function somehow contains also soft divergence. So my first look, a quick look at the definition in the SCET seems very similar to the definition of PDF. I don't see why the soft divergence will exist in your definition of collinear function.
Collinear function.
Yeah.
Actually, for example, if we consider the trade-off process like that, sorry, that. Yeah, here, actually, here is when you construct the factorization, actually, we can obtain the kind of formalism around the scale 2 times 1 minus 3, right? Also, this soft function can be has been expressed in terms of soft reasonableness. The problem actually happens. Actually, these soft functions involve some infinite diagrams, right? So I just point out that this collinear function wouldn't be standard particle distribution functions. Actually, around this scale, we have to worry about some kind of count problem. Okay. So from this collinear part 1 calculations, we have subtracted some kind of soft contributions from there. And then when we combine that kind of stuff, we can obtain the consistent particle distribution function like that. So
this is soft function. This additional soft function is induced because you do the two-step matching, the SCET1 and SCET2.
yeah.
Okay.
or maybe it's above the scale Q times 1 minus G. Actually, this collision study is defined at the low end scale than Q times 1 minus G. Actually, that gives a difference.
Excuse me. There are results for summing of logarithms in the Gaussian cross section with threshold logarithms of 1 minus C.
Yeah.
That go back quite a long way before SCET.
Yeah.
A lot of them do George Sturman, for instance. Are you differing in your answer from those, or are you just deriving the same answer in a different way?
Actually, yes, I can drive the same issue. Actually, the main difference, even actually here as I showed one calculation for the soft function, right? Yeah. Actually, this soft function involves some different diagrams, right? So in order to cure that kind of problem, actually I need to find the collinear function and I match the collinear function on the part of distribution function. Finally, I recombine the collinear counter and this soft function, and then the result is just somewhat interesting. I mean, here, originally this result is the same as the soft functions. Only difference is all the different diagonals in the soft function has been converted to UV diagonals. Okay? So actually the numerical result for the list formation in QCD doesn't change.
Sorry, it doesn't change.
It doesn't change.
I think this sort of this overlapping infinite divergence in these soft functions and collinear functions somehow related to this definitions of this proton state in this SCET. Actually, this is not a state in QCD because in SCET the proton is just consists of these three collinear quarks, so this doesn't correspond to the 4 QCD state, where this particles inside these protons can be actually soft, so you will get some sort of these problems. But actually, I have a question because you shuffling these soft functions and collinear functions and find out that there is certain combinations is somehow IR finite. So is this just similar to what EDB did? I think very recently, or because also you shuffling these soft function and collinear function and find out that if you just you just do some divide, if I remember correctly, divide the soft function into 2 pieces and then absorb these 2 different pieces into these 2 collinear function and separately you will get IR finite these universal non-independent functions. It seems to that you play the similar games here because you also just finally, you combine the soft piece and collinear piece together, and then you find that this W is actually IR finite. Right. This is, this paper by DB. This actually the correct definition of this transverse momentum dependent PDF is actually by EDB, which is claimed to be the same as this what Collins defined, and then he wrote a paper that is can decompose the sort function into 2 objects, and then you combine them into these collinear and anti-collinear functions, and it seems that they are really the same.
Yeah, I think it's similar. I agree with that. Well, actually, individual approach, actually, they just as individual and current, they just introduced the transpose dependent path distribution function, right? So they argue that actually state covers all the data efficient region. Okay. Here is I just actually as when they construct that kind of collinear functions, they just subtract the soft part. But actually this soft part, for example, for the here like that, actually they divide the